The next topic we cover relates to surfactants, their structure and their properties, mechanism of action of surfactants, surfactant solubility and formation of aggregates known as micelles, and different phases of surfactants in solution. Surfactants are amphiphilic or bifunctional compounds with a hydrophilic, means water-loving, and hydrophobic, means oil-loving segments on the molecules. Because of this amphiphilic character, they are known to orient themselves at surfaces and interfaces with hydrophilic part towards the aqueous phase and hydrophobic part towards the non-aqueous phase. The hydrophobic segment is often a linear hydrocarbon chain with 8 to 10 carbon atoms, usually sourced from petrochemicals or from natural fats and oils like coconut oil. The hydrophilic segment of the molecule is either electrically charged or a neutral polar head group. The schematics show examples of anionic, cationic, amphoteric, and non-ionic surfactants and their typical structures. Surface active agents adsorb on surfaces and interfaces and modify those interfaces. They can absorb at interface between solid and liquid or two immiscible liquids and liquid and gas phases. As a result, surface and interfacial properties are modified and processes such as wetting, foaming, emulsification, and detergency are improved. The fundamental properties of surfactants are orientation or absorption on surfaces and interfaces and formation of molecular aggregates. Here, surfactant absorption at air-water interface is shown. The hydrophilic part is in aqueous phase and hydrophobic groups are in the air. There are many examples of surfactants in action. One is in biological system. In our body, there is surfactant secreted from the bile, and which facilitates digestion of fats and greases by emulsifying them. Soap have been used as for a couple thousand years for cleaning and hygiene. This is the structure of the bile acids, and this is the structure of soap. Here is the mechanism of action of surfactants in aqueous solutions. Surfactants initially dissolve as monomers at very dilute domain, and then as concentration is increased, surfactants adsorb at air-water interface and reduce surface tension. As we further increase, once the air-water surface is saturated, surfactants form aggregates, spherical geometry aggregates known as micelles. The point at which these aggregates occur is known as critical micelle concentration. It's also the point that the surface tension reaches a minimum and basically stays unchanged. Here is another schematic, shows the same phenomena. Again, initially surfactants are in water as monomers, and as the concentration increases, surfactants adsorb at the surface, and at this point, this specific concentration of critical micelle concentration, which is specific to each surfactant, the micelles are formed, and we reach a minimum surface tension. This can be measured using an automated tensiometer, which is basically a precise balance, as it's shown here. And there is a ring that is pulled out of the liquid, and at the breaking point, the highest tension is applied to this balance, and that is measured as the surface tension at that point. We can look at the effect of concentration of surfactants as they reduce surface tension. Here is a schematic known as tensiogram. And as you see here, in anionic surfactant, sodium lauryl sulfate with 1 mole of ethylene oxide is added. And as the concentration of surfactant is increased, the surface tension of water drops from around 70 to down around 30 for this particular surfactant. This is now measured at different temperatures, and it can be measured at different water conditions. As you see here, the concentration covers a wide range from 10 to the minus 4% to 1%. And as we mentioned, at the point of minimum surface tension, the micelles are formed, and roughly this is the critical micelle concentration for this particular surfactant. Here is another tensiogram for a non-ionic surfactant, alcohol ethoxylate. Similar profile. Non-ionics have much lower critical micelle concentrations. They're more effective in reducing surface tension. We can take that data from the tensiogram and determine the critical micelle concentrations for each surfactant. We can measure the area per molecule of surfactants. So as you see here, CMC ranges in the range of 10 to the minus 4 to 10 to the minus 5 for these surfactants. The area per molecule is in the range of 40 to 50 angstrom. Here are typical values of surface and interfacial tensions for different surfactants. For example, anionic surfactants tend to have CMC in the range of 10 to minus 2 to 10 to minus 3. The non-ionic surfactants are orders of magnitude lower in CMC. Efficiency and effectiveness of surfactants. This is an important point in surfactant selections for different applications. The 2 factors are here from the tensiogram as we plot surface tension versus concentration of surfactant. The slope is an indication of efficiency of surfactant. So surfactant A here is more efficient than B. The minimum surface tension is an indication of the effectiveness. So B is more effective than A. Ionic and non-ionic surfactants display different phenomena in aqueous solutions. Ionic surfactants have a Kraft point. This is a temperature at which solubility increases sharply due to micelle formation. This is a triple point at which the solid hydrated crystals are in equilibrium with dissolved surfactant monomers. On the other hand, non-ionics exhibit a cloud point. This is a temperature at which the surfactants becomes dehydrated and creates two phases of micelle poor and micelle rich domains. Here is a figure that shows craft point. As you see, this is surfactant concentration versus temperature. The concentration increases sharply at this craft point. Phases of surfactant with increasing concentration, surfactant form rod-like. So we start with moving away from CMC, critical micelle concentration. We initially create spherical micelles, then at higher concentrations, this can change to rod-shaped micelles or hexagonal or lamellar micelles. Here's another picture that shows that as we increase concentration, we go from monomers, single molecules, to spherical micelles, to different phases of micelles, and eventually to a lamellar phase and liquid crystals. There's another picture of that, the phase diagram for different phases of surfactant. And of course, this is different for each surfactant. Again, we go from spherical micelles to cylindrical to hexagonal to lamellar. And eventually, at low temperatures and high concentrations, we have crystals. This is an interesting concept that relates to non-ionic surfactants. There is a wide range of alcohol ethoxylates, primary non-ionic surfactants in commercial use. And the reason for that is it's possible by careful selection of raw materials and choice of reaction conditions. We can vary the chain length of hydrophobe and the hydrophil. And the balance of the hydrophobe and hydrophil is known as HLB, hydrophobic lyophobic balance. And depending on what this ratio is, we have different applications for the non-ionics. This table here shows how this HLB value relates to the application property. So when HLB is between 0 to 3, meaning that we have predominant hydrophobe segment, these are insoluble. They're mainly used as dispersants and defoamers. In the range of 3 to 6, they're used as water and oil emulsions. HLP 6 to 8, we get a milky suspension, and which are used as wetting agents. 8 to 10, again, wetting agents. 10 to 13 is the kind of surfactants that are used in cleaning systems and in detergents, and so on.